Our speaker today is Tatum Rask, and she will be talking about the Poincaré duality for persistence diagrams of generalized cofiltrations. Take it away.
Awesome. Thank you so much for the introduction and for the invitation to speak. Yeah, as Teresa said, I'm really excited to share with y'all a Poincaré duality result that is some joint work with me and my advisor at CSU, Amit Patel. So let's jump right in it. And just to emphasize that I am more than happy to answer questions as they come or towards the end, whatever makes you feel most comfortable. But what are we going to talk about today? We're going to start with an overview on how we're going to be computing persistence over posets in this talk. This section is mainly background work. And then after we go over how we're computing persistence over posets, we're going to introduce this notion of a cofiltration. And then associated with every cofiltration, a little bit of a spoiler alert, there is a dual filtration that we will introduce. And using the tools from those first three sections, we are going to be able to state and give a quick sketch of our proof of Poincaré duality. I'll finish with a couple examples so we can see this in action, and that will be it. So let's jump right into persistence over posets. And I just want to start by giving some definitions for posets that will help us understand the talk later on. So in this talk, we're going to be working with finite posets. That's just so I don't have to go into some technicalities that I don't want to go into the weeds with today. So given a finite poset P, I'm going to be drawing a Hasse diagram, which you kind of see on that top right corner. The Hasse diagram, you can read off the ordering of our poset. So if we have this poset P, we read from bottom to top, and the lines tell us anytime there is a relation. So in P, A is less than or equal to B, A is less than or equal to C, and then we also assume transitivity, so A is less than or equal to D as well. Also, given a poset P, we can define its interval poset, which is the poset of all intervals A to B, where A is less than or equal to B. And the ordering I'm going to put on this interval poset is the product order. So A is less than or equal, AB is less than or equal to CD. Well, if the ordering on our underlying poset is preserved component-wise, so A is less than or equal to C and B is less than or equal to D. This poset is going to show up quite often in this talk, as well as its interval poset. So I have the interval poset on the screen. Eventually, we're going to see functions defined on this poset where you won't see the intervals, but I'll be sure to call out the intervals when something interesting is happening. So we can connect these intervals to the functions we define. And so the reason I'm giving all this background on posets is because we are going to want to study a filtration over a poset. So if we have some simplicial complex, let's call it K, we can filter that simplicial complex indexed by a finite poset. So a filtration is going to be a functor from that poset to this category delta K, where this category is the category of subcomplexes of K. So every object is going to be a simplicial complex, and then the morphisms are just going to be inclusion maps between them. So since it's a functor, this means that the inclusion maps have to respect the ordering from our poset. So as we move up in our through our poset up in our Hasse diagram, we'll see that we have inclusion maps between our subcomplexes of K. And because we're applied topologists, we want to study what happens to the topology of our space, specifically the homology, as we move through this filtration. So we're going to do that by looking at certain functions defined on these filtrations. And I'm going to introduce two different functions that we might be interested in studying today, two different approaches. The first is called the birth-death function. Now, this is a function defined on the interval poset. And what the birth-death function does is it looks at A and B, and we're going to look at the cycle space at A, and we're going to intersect that with the boundary space at B. This is called the birth-death space. But this birth-death function is just going to assign to an interval AB the dimension of our birth-death space. So for the filtration below, we can compute the first, the one-dimensional birth-death function, which you see on the screen. I want to point out that this kind of captures our intuition. The kind of first one we see, so the lower one we see, is the interval CD. So that's that leftmost, like middle step in our filtration where we see a cycle appear. And then we also get a 1 at the interval dd because that cycle is in the cycle space at d. Right. Now, another approach we can take involves using persistence modules. So instead of computing these birth-death spaces and finding the dimensions, we could start with a persistent module. Right, often we get a persistence module by looking at homology at each step in our filtration. And once we have that persistent module, we might want to get something similar to what we had previously with our birth-death function. So in order to compute the birth-death function for a persistence module rather than just a filtration, we have to first find a free presentation of our persistence module. So what is a free presentation of a persistence module? Well, we're going to start with another persistence module indexed by the same poset. And this persistence module has to be free, which means is going to be a direct sum of these free modules here, where this f upper A is defined as follows. So with that element in our poset A, f upper A is going to assign to every element B in our poset, while our underlying field F, if A is less than or equal to B, 0 otherwise. And then all the morphisms are going to be either 0 maps or identity maps. And so once we have this module M, we have a surjective natural transformation from our free module M to our persistence module. Right, so here's an example. If we have our persistence module coming from the one-dimensional homology of our filtration, I've drawn to the right of our original persistence module, that free module M, and now there's a surjective natural transformation from our free module to our persistence module. All right, and so the reason we define these free presentations is because the birth-death function, as defined a few slides ago, doesn't quite work well with these persistence modules. Once we have computed homology, which we often do when creating these persistence modules, we lose information about what the cycles and the boundaries are. So once we've created this free presentation, this actually gives us the tools we need in order to compute a new birth-death function, a birth-death function for this persistence module. So it's defined very similarly. You're going to look at your free module A, and then intersect, your free module M. Look at that first, the left-hand side of your interval. Look at the free module at that left-hand side, so in this case A, and then intersect it with the kernel of the component of our natural transformation at B, so the endpoint of our interval. And then just like we did with our birth-death spaces, we're now just going to take the dimension of this intersection in order to get the birth-death function at the interval AB. And so with the kind of running example we've seen, here's what the birth-death function of our free presentation looks like. I want to point out that this is exactly the same function that we got when we looked at the birth-death function just coming from our filtration, so looking at cycles and boundaries rather than free presentations of our persistence module. And that is no coincidence. I'll get to that later, but before we get to just some facts about how all these different functions relate, I want to point out that the functions we saw earlier, so the birth-death function for a free presentation or for a filtration, tells us cycles born at or before A that die at or before B, but we might want to know precisely when these cycles are born and precisely when they die. So in order to do that, we are going to Mobius invert our birth-death functions. So this will work for either the persistence module case, so when we have the birth-death function of our free presentation, or it'll also work for our birth-death function for a filtration. The Mobius inversion of just any, let's say, integer valued function on our poset is defined with the following equation. So the Mobius inversion is the function inside of the sum here, and is the Mobius inversion of our birth-death function, which is on the left-hand side of our equation. I'm highlighting this equation because I want to point out that the Mobius inversion is also known as the combinatorial derivative, because if you kind of stare at this equation a lot, it looks a lot like a discrete version of the fundamental theorem of calculus, right? It looks like we're integrating the derivative and we get back our original function. So often this is called the combinatorial derivative. And kind of with that intuition, it tells us not only the cycles that are born at or before A that die at or before B, but it tells us precisely the cycles that are born at A and die at B. So here we see, again, this 1 in our persistence diagram tells us that there is a cycle born at time C that dies at time D. Right. I'll pause here for any questions about computing persistence. This pipeline is going to show up again, but this is the most in-depth I'm going to go. All
I think
right.
so far, no questions.
Awesome. Real quickly, before we move on to cofiltrations, I want to make some observations. I hinted that for the specific example I looked at, our birth-depth function for a free presentation gave us the same exact thing as our birth-depth function just for a filtration. Now, that's not always going to be exactly true, but we still get that these methods will give us equivalent persistence diagrams. Moreover, even if you take two different free presentations, once you compute the birth-depth function for those free presentations of the same persistence module, and then you Mobius invert to get your persistence diagrams, these are going to be the same off the diagonal. So in this case, we say that these persistence diagrams are equivalent. And again, we can either start with the filtration and compute the birth-depth function of that filtration, or we could compute a persistence module, find a free presentation, and then compute the birth-depth function. And it turns out, again, these methods are equivalent. Moreover, that means that once we compute the Mobius inversion of these two functions, they're going to be the same off of the diagonal. So with that in mind, let's move to introducing cofiltrations. And so again, just like we did with filtrations, we're going to start with a simplicial complex, but instead of looking at subcomplexes of that simplicial complex, we're going to look at what we call soup complexes. So soup complex of K is going to be a closed upward subset of K. Again, this is kind of dual to the notion of a closed downward subset of K that gives us our subcomplex. And more precisely, this is going to be a subset of K such that if I have a simplex in my soup complex and I have a coface of that simplex, well, that also must be in my soup complex. So what we see on the screen, the two pictures I have are two examples of soup complexes of the standard 2 simplex. In this talk, I'm going to use dashed lines to represent an edge that's not there, but exists in our total space, our entire simplicial complex. And I'm going to use non-filled in circles to represent vertices that are, again, in our total space, our simplicial complex, but not in our soup complex. And just some observations before we move on to entire cofiltrations. So if we have a soup complex of K, well, it turns out the soup complex is just some complement of a subcomplex. That's not too difficult to see, right? If we have a closed upward subset, its complement is going to be closed downwards. And so we can use this observation to help us compute cohomology or homology. If we want to look at chain spaces or co-chain spaces of our soup complex L, we can compute this by looking at relative chain or co-chain spaces, where we look at our entire simplex relative the complement of our soup complex. All right. And so now we can define a cofiltration in pretty much the exact same way as we define a filtration of a simplicial complex. So again, it's going to be a functor from our finite poset P to now the category of soup complexes of K, this nabla K category. No surprise, but the objects are going to be our soup complexes, and the morphisms are again going to be inclusion maps. And just like we did with filtrations, we want to study how the topology or the homology of our simplex changes as we move through this cofiltration. And so we can define the birth-depth function. I'm going to describe the birth-depth function for a filtration. You could also define the birth-depth function for a persistence module. And that would work just like it did in the previous background section. But I'm just going to go more in-depth into this birth-depth function for our filtration. So again, it's going to look almost exactly the same, but there's a subtle difference. Here we are computing the birth-depth function using cocycles and co-boundaries. So our birth-death space now is going to be our co-cycles at A intersect our co-boundaries at B. And then our birth-death function is just going to assign to an interval AB the dimension of that birth-death space. So again, here's one example. We could look at the cofiltration I have on the screen and compute its birth-death function, looking at 1 co-cycles and 1 co-boundaries. And then just like before, this tells us which co-cycles are born at or before A that die at or before B. But we want to know precisely when these co-cycles are born and when they die. So in order to get that information, we are going to Mobius invert. So again, we're going to use this fundamental theorem of calculus looking definition to find the Mobius inversion of our birth-death function, and this will give us our persistence diagram. And so moving on to our next section on dual filtrations, I'll give a little bit of background that once we defined these cofiltrations, we kind of knew there was going to be some way to connect the cohomology of cofiltrations to the homology of filtrations. Right, the two seem very connected. First of all, we know that homology and cohomology are connected by a Poincaré duality, hence the title of this slide. And we also know that soup complexes and subcomplexes are very much related. You don't get anything like just for free, right? The persistence diagrams coming from a soup complex and then looking at, the stuff you deleted to get a filtration. Those aren't going to give you the same persistence diagrams. But once we define something called dual filtrations, we can finally make our Poincaré duality statement. Okay, so if we have a cofiltration, how do we define its dual filtration? Well, again, we're going to start by looking at all the soup complexes. So if we have a soup complex of our simplicial complex K, we can define its dual subcomplex as follows. So this dual subcomplex is going to be a subcomplex of the barycentric subdivision of our simplicial complex K. And we build this dual subcomplex by, well, let's look at every single subcomplex, every single simplex that appears in our soup complex. And then we're going to throw into our dual subcomplexes all the chains that start with that simplex. So all chains that start with simplices in our soup complex. Now this is actually going to be a subcomplex, right? Because our soup complex is closed upwards. So any subchain of a chain that starts with a simplex in L is also going to be in our dual subcomplex. So this is closed downwards. It actually is a subcomplex of our barycentric subdivision. And here we see one example of that. I have on the left-hand side of the screen a soup complex of our standard 2 simplex. And then on the right-hand side of the screen is its dual subcomplex on the barycentric subdivision. All right. And one observation that's going to be crucial later is that if we look at the underlying space of our dual subcomplex, that's going to be a deformation retract of the underlying space of our original soup complex. So one way to see that is let's compute our dual subcomplex. And then let's look at the open star of that dual subcomplex in our barycentric subdivision. So I've drawn in purple the open star of this dual subcomplex. And in general, this isn't going to be exactly like the subdivision of our soup complex. In this case, it is, but it's always going to be a deformation retract of the subdivision of our soup complex. And so now we know what to do with soup complexes, and we can do this for an entire cofiltration. So if we have a cofiltration of a simplicial complex K indexed over a poset P, we can define its dual filtration as follows. So now it's going to be a filtration of the barycentric subdivision of our simplicial complex, and it's going to be indexed over the same poset P. If we fix an element in our poset, what subcomplex are we going to assign to that element? Well, you're just going to look at the dual subcomplex for the corresponding element of our cofiltration. So again, here's one example. We have a cofiltration of our standard 2 simplex on the left, and then its dual filtration on the right. Right. And it turns out this is really all the tools we need in order to make our Poincaré duality statement. So here's the statement in its full. If we have a triangulation of a compact F-orientable M manifold, in this case without boundary, and then we have its barycentric subdivision, we can compute a cofiltration of our triangulation and then find its dual filtration. Well, then it turns out that the persistence diagrams coming from first the ith cohomology of the cofiltration, well, that's going to be equivalent to the persistence diagram coming from the m minus first homology of the dual filtration. All right, I'm going to pause on this slide for a little bit before we get into a proof sketch. And so I guess now would be a good time to see if anyone has some questions on this slide or anything previous.
I would have a question on the barycentric subdivision. You just go one level down, or how much do you subdivide?
Yeah, so you just have to subdivide once.
Okay.
Yeah, so here we just have, yeah, here we just subdivide once, so we're really,
Yeah. Okay.
good question. All right. So now would be a good time to point out we also have a version of this where we start with the filtration and you compute its dual cofiltration. We again get a similar Poincaré duality statement. I'm not going to go over that today because the math's pretty much the same. But at the very end, I'll have a QR code to our paper if you want to look at the opposite case, filtrations, cofiltrations, like that. I do want to give a quick sketch of this proof because I don't think it's too bad and it's kind of fun how it uses all these tools that I introduced. And it fits on one slide, which is pretty nice. So here's kind of how the proof works. Of course, we're going to use classical Poincaré duality. So right, if we have an F-orientable M manifold without boundary, here I'm not requiring that this manifold be compact. And so in this case, if we have ith cohomology with compact support of our manifold, that is going to be isomorphic to m minus first homology of our manifold. And from this classical version of Poincaré duality, we get that the persistence module of our ith cohomology with compact support of our cofiltration is isomorphic to the persistence module coming from m minus first homology of our cofiltration. One thing that I want to point out that I did not earlier is that this cohomology with compact support ends up being exactly the cohomology that we are computing when we're computing cohomology of our soup complexes. And so once we have that, we know that the underlying space of our soup complex for every single step in our filtration is going to be homotopy equivalent to the underlying space of its dual subcomplex for the same element in our post set. And so because of that, we know that m minus first homology of our cofiltration, that persistence module is going to be the same as the persistence module of m minus first homology of our dual filtration. So we already have that these persistence modules are the same. And now how could we compute these birth-death functions? Well, we know that we can find free presentations of these birth-death functions. And we've already seen that if we have the birth-death function of these free presentations, well, it doesn't matter if we use these free presentations or if we just go to our original filtrations and find the birth-death function as defined for those filtrations. We know that these persistence diagrams are going to be the same up to the diagonal. And so what we get from all of this is that our persistence diagram coming from ith cohomology of our cofiltration is going to be equivalent to our persistence diagram coming from m minus first homology of our dual filtration. And again, what do I mean by equivalent? That just means that the persistence diagram is the same up to the diagonal. And that's just a quick run through of the proof. But perhaps what's more fun is looking at a couple examples. The first example I have is, let's look at a cofiltration of a triangulation of the torus. In case it's a little bit hard to see, I'll quickly describe what we see in this filtration. At step A, so at the very bottom, we have just the faces of our triangulation. As we move up a step, you can see that I've included all the edges in both the step B and the step C, but there are certain vertices that are still left out. Once we move to the top step, we see that everything is present. We have the entire torus. So now let's compute the dual filtration. I really just like showing this slide because I had a lot of fun making this picture. And I think it's pretty wacky and pretty fun. But here's what the dual filtration will look like. And now we can ask, how do the persistence diagrams relate? Because of this theorem, we expect that the persistence diagrams are equivalent, so the same up to the diagonal. And we can actually see that in practice. So here are the persistence diagrams. You'll see that the zeroth cohomology diagram of our cofiltration it turns out exactly the same as the second homology diagram of our dual filtration. But once you move to dimension 1 or dimension 2, when you're looking at cohomology of your cofiltration, you can see that the diagonals start differing. I want to point out that that's not surprising. If we zoom in, let's see if I can get my highlighter. If we zoom in right here, let's say, we have a lot more simplices in our barycentric subdivision. So it makes intuitive sense to me that we would have a lot larger numbers on the diagonal here than we did when we were looking at second cohomology of our cofiltration. All right. So there's our first example. We could also look at a slightly smaller example. We could look at a cofiltration of now a triangulation of the two-sphere. I'll let us stare at this and take it in. For this example, the dual filtration isn't as wacky, but it's still a little fun. So here's our cofiltration of the two-sphere. And then here's its dual filtration. So again, a filtration on the barycentric subdivision of my triangulation of the two-sphere. And again, we can compute persistence diagrams, and we can see, just like we did with the torus, there are some persistence diagrams that are exactly on the nose the same. There are some persistence diagrams that are the same up to the diagonal, but all this just shows what we want to show. It shows that our theorem, it shows our theorem. Right. And that is really all I want to share with y'all in terms of the math. Here are some references that I've selected. These first 4 references really give a good deep dive into some of the theoretical background, specifically that section 1 on persistence over posets that I went over. So if you want to look more into kind of that pipeline, I recommend looking at these papers, specifically Aziz and Alex's Galois connections in persistent homology. I also want to point out some related work. So this project was really inspired by this dualities and persistent cohomology paper. We wanted to know if those dualities held in the multi-parameter setting. And that's kind of how we came at this whole notion of cofiltrations, dual filtrations, and all of that. I also want to point out some related work. This paper, I haven't had the time to read in depth, but I would really like to, called Cofiltrations of Spanning Trees in Multi-Parameter Persistent Homology. Be really cool to see some examples of cofiltrations showing up, especially in applications. Thank you all for your time and your attention. Now would be a good time to ask for more questions. You can also follow you can scan the QR code on the screen to see, that'll lead you to the paper. But yeah, thank you again. Are there any questions?
Thank you very much. Let's please all unmute ourselves so that we can thank Tatum together by clapping. Nice. It was a really nice talk. I loved your illustrations and your examples. It was great. Yeah, let's start with questions right away. Does someone have a question?
I'd have a question, if I may. Okay, my first question, could you go 2 slides back? Or maybe
Yeah.
3, I think 2. Yeah, this one. So on the, let me see. Well, we know that the diagonals in general differ, but in both of your examples, the zeroth cohomology, so the picture up left and the picture down right, they're identical in both examples. Like, is it just because the example is sort of easy, or can you sort of tell how difficult or how complex do you have your example to be in order for the numbers to differ?
Yeah. So I don't have a super precise answer. I don't know for sure when they're going to differ or when they're going to be exactly the same, but I can tell you why in these specific examples, both of them are exactly the same. And that's really just due to how I created these examples. So if we look at the cofiltration, you see that nothing zero-dimensional shows up until the final step. So there are no zero-dimensional cocycles to look at because we don't have, okay, that's not entirely true because we do have vertices showing up here. But it turns out that there'll never be co-boundaries until we reach this top step. Perhaps what's easier to see is when we go to our dual filtrations. This is true for both examples. No two-dimensional homological features show up until that last step. We don't have a void showing up until everything is connected for the sphere. And then the same is true if you look at this filtration for the torus. Yeah, so I think the dual filtrations make that really easy to see. Nothing two-dimensional shows up until the very last step.
But wait, if you would have, I mean, like a two-dimensional homology would only show in case of two-dimensional manifold if you take the whole manifold, right?
Yes. Yeah. Yeah.
I mean, I guess in theory, the manifold could be a union of 2 manifolds, and then you could
sure.
one of the 2
But
manifolds.
let's
But
say,
like if it's say connected or so.
Yeah, let's say we would keep it sort of, simple.
Yeah.
Yeah, never mind. It's something to, I have something to think about now. Thank you very much.
Yeah. No, that's a really good question. I wonder if you could say something like your top dimensional thing / also zero-dimensional thing will always be super simple if you have just like one component, maybe.
Yeah, but you do consider manifolds, right? I mean, that was the
Yes.
So one could also assume from beginning that it's anyway like a connected manifold, because otherwise you can always work on the connected component.
Yeah.
And then you always have only, I don't know. Maybe it's something for you to think about as well.
Yeah. No, that's a good question. Thank you.
No problem.
Right, let's continue with the next question by Jose.
Hi, Tatum.
Hi.
So I have the following question. So in Poincaré duality, you need this hypothesis of R orientability. So I was worried that sort of in your theorem, you only require orientability of the full manifold, but nowhere else along the filtration. So again, my worry was something that sort of became, that started today, let's say orientable, then became non-orientable, and then it became orientable again. But it sounds like that's not a problem. Is it because your presentations, your free presentations only care about the sort of the manifold in a sense? Yeah, why? Yeah.
Yeah, so I'll point out something that I think is really cool is that I want to say we use, at least in this statement, we apply Poincaré duality just to our cofiltration, so we don't have to worry about this with our dual filtration, in case that hadn't occurred to you. And so it turns out with the, with the way that the cofiltrations are constructed because of this soup complex condition, turns out the orientability, you're not going to get something along the way that's not orientable, because of the way that because of the way that you construct these soup complexes.
I think one way to think about that in the manifold setting is like unorientable would be if you have a path where you could walk around that path and now you're on the other side, right? Well, if you could have that at one stage in the filtration, that path will still be there, even if the surface gets larger.
Yeah, but like, for example, if you start with say with a circle that then becomes the equator of a Mobius band, so you went from orientable to non-orientable, and then you fill in, let's say, like a filled-in torus, like an S1 cross D2. So
Changing the dimension.
Right. So I mean, there didn't seem to be any requirements about dimension. So again, so that went from orientable to non-orientable to orientable again. And I would have guessed that you needed to keep track of that if you wanted to use Poincaré duality in a persistent setting. But again, it sounds like this is not a problem.
Yeah, so at least with that example, with the way that cofiltrations are defined, you have to be closed upwards. So if you have, in this case, we're always going to have two-dimensional things. We're always going to have like these 2D surfaces, these spaces. And so if your overall manifold is two-dimensional, anytime you add something in, you have to have something two-dimensional so that you maintain that closed upward property.
Okay. Yeah, I'll have to think about it. But yeah, thank you.
Yeah, and we can chat offline as well.
Okay, and then we have already a next question by Georg Essel.
Hi, thank you so much. Fascinating talk. Maybe you've actually just answered my question in a way, in that you had this restriction that you don't have boundaries, but you just said you have a max dimensional object. I guess that's your boundaryless object. But in between, like in a way, I'm mirroring a different concern that Jose has. You have these objects that are clearly bounded. So that's not an issue also, apparently.
Yeah, so again, that comes back to how these cofiltrations are defined. If you start with something without boundary, because you need it to be closed upwards, as soon as you add something of lower dimensional, so we have two manifolds, as soon as you add something one-dimensional, well, because this manifold doesn't have boundary, you're going to have some faces, some two-dimensional things to add back in. Now, of course, what you might have noticed is that once we define these filtrations, we do have boundaries. These things aren't even manifolds, because if you look in like right here,
in a way that sort of segues into another question I have, which is, you talked about that this really works on the level of filtrations, which I read to mean that you can do this purely combinatorially. You don't actually need a field or any sort of coefficients. You can just do this. Is that the correct reading of what you said?
Let me see. What do you mean by you could do this combinatorially?
Well, filtration in the sense of, post-set inclusions or something, where yes, you have some post-set structure, but you don't actually have, numbers assigned that say, oh, it's this much bigger than the other or something, but you really have just a combinatorial object that gives you something like inclusions. And so then in my mind, it would be combinatorial, right? You don't actually work with necessarily some sort of ring or field coefficients.
Yeah, that is a really good question. That is actually something I would love to look into in the future. You would have to do some tweaking of scrolling the wrong direction. My apologies if anyone's getting like all turned around. I would really like to look into that to find maybe a more like combinatorial or algebraic version of this. Right now, we do rely on this statement of Poincaré duality in order for this proof to follow through. But I wonder if there's some, instead of Poincaré duality, some combinatorial or some algebraic condition you could put on, say, your persistence modules or your posets to prove a similar result without relying on the geometry so heavily. So to answer your question, I don't know, but I think it would be really, really cool next step to look at.
Oh, super fascinating. Thank you so much.
Yeah, thank you.
Great discussion so far. Do we have some more questions? Oh yeah, Adam, please.
I guess just on that note of the combinatorial nature, I forget who authored the paper, but it was Amit and somebody else. Basically relating the what do you call it? Sorry, I'm blanking on words. The Mobius inversion, relating that to an Euler characteristic of a total complex. Could that be the combinatorial, I don't know, intermediate here?
Yeah. So just, I guess in case anyone else wants to look into this, I think the paper you're thinking about is Mobius homology. That's by Patel and Skraba.
Yes, that's the one.
Yes. You know, that's a really good question. Yeah, I have been looking into things related to that paper more recently, so that's been on the mind. And that would be a really cool result.
Yeah, likewise with yeah. So yeah, that's cool.
Yeah, I'll be thinking about that.
Yeah, it sounds like this is probably a question where the two of you should get together at some point to think about it more. Yeah, let's see if there's any more questions. We have so many like open-ended, difficult questions so far. No, no simple, basic questions. But it's great. Those questions like spark discussions. So, yeah. Then, if there's no more questions, maybe I'll end the recording here, and then maybe we can still ask some questions offline. Thank you again for a really nice talk.
Yeah, thank you. Thanks everyone for the good questions so far.